Okay, participants online, do you hear me? Can one of you please confirm?
Yes, sir.
Okay, so you know it is confusing for me. I see two S's, Shruti Singh and Shekhar Singh. Mrignab, were you there previously? I do not recollect interacting with you in the last 3 days. Have you been online?
Sir, is this a question to me? Hello? Is this a question to...
Mrignab
I didn't get.
Bhargav Saikia?
Yes, sir. So I'm actually an offline student.
Okay. Were you here the last 3 days for this course?
Yes, sir. Yes, sir.
And were you okay? So today you are doing online.
Yes, sir.
Okay. Problem driver pointer system. Yes. Give me 2-3 minutes. When we start, I want to make sure the people online will also benefit. I will wait 2 more minutes. Shashi, yesterday you wore pink, so I wore pink today thinking we'll match. And you changed. We'll see. Shh, don't tell others. These people all, they wore blue, didn't tell us. Okay, I'm going to start the session now. So, welcome back. Good morning. This is day 4 of our Gyan program related to road safety, data and emerging technologies. So, I had a question here from Ritvik to remind the audience, the participants of the problem driver notification system, right? Pointer system, yes. It is basically a centralized coordinated. I have a web link in my slides that will give you more information. It is basically a system, record keeping database system managed centrally in the United States by the National Highway Traffic Safety Administration, often known as NHTSA, NHTSA. These are to help each state manages their own driver's license information. So, this is a central database to help identify repeat violators, or let us say I got a license in state 1 and then I moved to another state and I want to get my license there. Do I have a history in state 1 so state 2 can look at it? For the commercial motor vehicle drivers, there is yet another one to look at it. So, that is a quick overview of what that is. It is a centralized database to identify high risk or repeat violators. And this is based upon the points or the citations, challans that they receive. That can be done more done. For example, tying up with the insurance industry who have much better information, but they are private. They seldom share their data, as I mentioned, because of the competitive things. The one other, okay, talking about insurance companies, data that I haven't talked about, but emerging data in the last 10 plus years, maybe 15 years, many insurance companies have initiated programs for people who they cover, insure, saying that if you opt into a particular system, we will monitor your driving, and if you are a good driver, you will get a discount. So, in olden days, it used to be olden days many years ago, they will give you a device that you mount in your vehicle. It basically captures these following critical data and several others: time, location, speed, acceleration, and abrupt accelerations, abrupt decelerations, both longitudinal and transverse. So, that is their way. They collect that data to analyze individual drivers about their driving profiles, and collectively many drivers, if they cover in a metro area or urban area, are there things related to certain areas where they have higher risk. So, if you are there, maybe your premium will go up. Nowadays, you don't need to have that physical device. You just download an app and it runs on your mobile phone. They can capture the same information. So the insurance industry has a tremendous amount of data that are valuable for our safety analysis. So unless you have a specific project that is funded by the insurance industry that is of interest to them, it's unlikely that we will get that level of detail on the data. So today's sessions, morning and afternoon, and so the slide deck that I have here has 68 slides, so it's much longer than the others. I don't anticipate going through all of that in the morning and the afternoon, so it is to combine, and then it will lead into the session tomorrow. If depending on how much progress we make today, I will address some of these topics that I would have otherwise covered or touched upon tomorrow. I will do that today. Any questions, comments, feedback from the participants? Ritvik, were you able to get the survey results?
Yes, I shared you the link.
In was that email or how did you share it?
On WhatsApp.
Okay, that's the problem. I didn't look at the WhatsApp. Okay, I'm sorry. Yeah. Okay, I will see when I get a break. We'll see. Any other comments, feedback? All right. So, as always, I try to outline what we should try to get out of this session, this afternoon session, and a little bit into tomorrow morning session. We've talked about many ways, many sources of data. We've talked about some indicators of data, of safety, such as crashes, fatalities, injuries, the CAPCO scale. Excuse me, but there is more. So we'll get a little more about that. And we've already addressed some of the critical factors, but how do they tie to some of the things that we're going to address today? What are some ways to model or analyze the data? I'm not going to get into details of mathematical modeling. I will just try to give you a feel for what are the types of approaches. That will be later today or early tomorrow. But and issues related to data integration, we've seen several things. You've tried to work with one data set. In today's tutorial, I'll add a second data set which relates to fatal crashes, only fatal crashes, but there's a lot more detail compared to what we've seen over the last 2 days in our tutorials. And how do you tie all of these together to come up with a basic safety analysis framework for safety analysis? I mentioned in my discussions that traffic crashes are the leading cause of preventable deaths in the United States, and I wanted to show you the actual data. This is from a health agency. So what you see here, preventable deaths are less than 2 years of age, less than 1 year of age, and all the way up to the age 44. Traffic related unintentional injury, which is essentially traffic, is the leading cause. So the top you have columns for ages, and the rows are the rank, how high, and this is based upon 2021 data. So you see all the way from 1 to 4, 5 to 9, so on, up to 35 to 44, traffic crashes are the leading cause. Then in 2021 when they reported it, this went down to rank 4, even though the number of fatalities dropped just a little, 36,000 to 31,000. That's a 5,000 drop, which is substantial. But why did it go to rank 4? Because of COVID and COVID related. COVID became the first, and because of COVID, number 2 and number 3 got exacerbated because of complications related to COVID. So otherwise, even for age 45 to 54 and 55 to 64, all the way, so from age 1 to 65 or so, traffic related causes are the leading preventable death. And in the United States, just so that you know why 65, most organizations allow people to work at least until the age of 65, if not longer. So people are driving are very active. And for older ages, traffic goes down, the exposure is much lesser. Driving, they don't drive as much compared to when they were working or when they have families driving their children around, so on and so forth. So this is something I wanted to touch upon. The other thing that I wanted to talk about, how many of you have not heard about the Hayden's matrix? If you have not heard about the Hayden's matrix, oh wow. Online, if you have not heard about the Hayden's matrix, please raise your hand. Okay, Aishwarya, I saw you briefly raise your hand. Pratyush, okay, there are a few. Basically, this came about 50 years ago, more than 50 years ago. Is if you look at the matrix, you have columns which are pre-crash, during the crash, and post-crash, and on the rows are human factors or travelers. This basically user behavior. Second is vehicle and equipment. Third is road and environment. I apologize for these not lining up. When I changed the format for the slides, it just got skewed a little. This is what Professor Maurya was telling. Some things may get, but you know that these are the 3 rows. But what we can do essentially as traffic engineers for the most part is looking at pre-crash and road and environment. During crash, how do we design the roadside hazards or safety clear zones? And if the goal is vision 0, what we need to focus on is pre-crash. What can we do to avoid a crash? So Hayden, Mr. Hayden worked for the Insurance Institute for Highway Safety in the United States. That's an institute that is funded by many insurance companies. They look at their interest to look at. So if you look here, there are things related to road design, road operations, road maintenance, and delineation. So these are all design related pre-crash that an engineer does. We don't have much control over weather conditions, but we can design the roads. If there is a place in Northeast you have a lot of rain, make sure that the pavement is designed so that you drain the water off of the roadway surface. But in terms of other pre-crash, where we can have a difference is the human factors of travelers. We've talked about attitudes, driving under the influence of drugs or alcohol. We didn't talk much about driver skills or vision, but those are critical. That's why they make you go through a driving test, a skill test, to demonstrate that you can safely operate the vehicle. Vision, they make you do an eye test to look at that. And vision is tied to totally unrelated to what we have talked about. I won't touch upon it much. How do we decide on the sign, colors of the signs, the contrast of the signs, the sizes of the signs, lighting, so on. So all of that has to do with vision. And there is a good number of road users of the population who are colorblind. So they may not be able to differentiate between blue and green. So we want to make sure that the colors that we use, black on yellow background, black on white background, these are very clear contrast. So this is something, those of you, if you have an interest in safety, please look it up. There are lots and lots of references to it, but there are some summaries that you will be able to read in about 15 minutes to 30 minutes that will better inform you. But the point is, we also need to work with the mechanical engineers and others who do the vehicle design, vehicle size, and we take into account the impacts of vehicle statics, vehicle kinematics, whether it is traffic signal design, roadway design, curvature, width of lanes, shoulders, parking, so on and so forth. So there are a lot of interdependencies. This is, I gave you a conceptual schematic figure yesterday, then I gave you another one which said 10 to the power of 12, 10 to the power of 8, 10 to the power of 6. These are actual data from 2015 and 2022. So if you look at the bottom of the pyramid, there were about 13 million crashes. About 1/2, 50% were police reported, which means there are 50% even in the United States that are not reported. So that's why this is an estimate. And of these 6.3 million, 4.6 million, so about 75% were just property damage. 1.7 million were injury crashes, and then you have this includes the A, B, C, and the fatal crashes, there were 32,000 crashes, but more fatalities because there may be multiple fatalities per crash. And if I look at the 2022 data, then this pyramid is for 2015, 2022 data was slightly lower, but overall the societal harm when we talk about billions of dollars, people are not able to get a sense for what does it mean. I am just going to use rough numbers here, $240 billion economic cost. The US population is approximately 330 million. So what does it cost per person? 240 billion divided by 330, or 240 divided by 0.3. That's per person per year. So that's just the economic. If I use the societal harm, it is 3 times that, 3.5 times that. So you're looking at tens of thousands of dollars per person due to adverse safety outcomes. So this is something I wanted to recap what we talked about in the last few days. So here's a quick assignment, team assignment. Ritesh, you need to come sit with Shashi. I'm going to make you move forward as opposed to have Shashi go back. Those of you who are online, please connect with your WhatsApp groups. I know Ritvik sent a message yesterday. I don't follow the WhatsApp group when I'm in class. You were in group 1, right? Yeah. So Ritvik was participating with the WhatsApp group 1 when he was online day 1 and day 2. He's here in person, so he will not be participating with group 1. So all of you, it's a very simple problem. I'll give you 30 seconds. There are 2 districts that we are analyzing, wherever it be, whichever state. One district had a total of 1,000 crashes, the other district had a total of 1,020 crashes. Which of the 2 is safer and why? I'm going to give you 30 seconds starting now. Talk to your neighbors. Five seconds to go. Okay, time. WhatsApp group 3, what did your group come up with? Which is safer? Group 3? Nobody speaking up. Okay, WhatsApp group 4? Come on, people. WhatsApp group 5?
So just looking
Yeah.
at the number of crashes, it is very difficult to comment on that.
Yeah, this is the only information you have. You are a district collector, you were talking to the people, the population, people are complaining there are too many crashes, it's not safe. The superintendent of police, DSP, comes up and says, sir or madam, here are the total crash numbers. So that's all the decision maker had at this point of time. So I know you said it is difficult, but which is safer based on the data you have?
So based on just the data, A is safer.
A is safer, okay. WhatsApp group 5, that was group 4, right, Pratyush?
Yeah, sir.
Group 5? WhatsApp
I
group,
think,
yeah.
hello sir, good morning, Chandrika here sir.
Yeah.
Total 1,000 crashes, I think it's lower, so
It is
because
better?
we don't have another.
Okay, smaller
Yeah.
number is better, okay, thank you. WhatsApp group 1? Okay, WhatsApp group 2?
Hello, sir.
Yes.
Sir, option B is safer, sir.
Option B is safer even though it had more crashes.
Yes.
Okay. What makes you say that?
WhatsApp group 3, sir.
So maybe when we divide by the population, maybe
No, I didn't give
considering
you
the-
anything. The 2 districts have about the same population, same number of lane miles, lane kilometers, traffic volume. Everything else is approximately the same for the 2 districts. The only difference, significant difference, is the number of crashes.
Okay.
Sir,
Then maybe
divided by 365 and divided by 5 years.
Okay, that is all right. That will give you per day. My question is very simple. Which is safer?
1020.
1020 is safer. Okay, that's high crash. All right. WhatsApp group 2. Was that group 2? I think group 1 did not.
yes, a
respond.
group 2 just now.
Yeah. All right. In here, so I see, I want the 2 of you to sit together. Asagri, what did your team come up with?
I think If this is the only metric, then A is
A is better? Okay.
Safe.
All right. Ritesh, what did your team come up with?
Sir, I think none of them is safer. Both are disastrous.
Okay, one life is one too many. Okay. Sayantan?
Yeah, so in our opinion, that's the same because no one is safer because it has 1000, it has 1020, only 20 is the difference.
Okay.
So nothing is safer.
Aapka team?
So we believe from these numbers A is safer, but so the thing is, unless until we classify them into carbo scale we talk about,
Okay, so
Then
A is
only we
safer. All right.
then only we can decide.
All right. Pratyush, you also said that you needed more information. What information do you need, Pratyush?
Firstly, the severity of the crashes, like the crash can happen in anywhere. The severity of the crashes, the population, the
Okay, so
kilometers traveled in those things.
I understand. Okay. I knew you would ask this question. So, everything is the same in these two districts. The population is almost identical. The age distribution of the population is almost identical. The gender distribution of the population is almost identical. All right. The travel demand, the supply are all identical. The only difference is what I am just showing you. The same number that I showed you on the previous slide, I am giving you a breakdown on the Capco scale. Now, I will give you 1 minute for your teams to discuss and tell me which one you think is safer and why. Starting now. All right, 5 seconds. Okay, time. Anuj and Rijul, what did your team come up with? Be very brief. I don't need a long essay. In 10 seconds, tell us.
District 2.
What. District 2 is safer. Why?
So because major injuries is less.
Major injuries is less. Okay, which specific number are you looking at?
A.
A, 36 and 19. Okay. All right. Ritwik? A, B, C are different types of injuries, A being the most serious, life changing, B is moderate, C is minor, O is property damage.
I choose to live in district
2. You choose to live in district 2, okay.
District 2 is safe, sir.
Safer?
Yes.
All right. How about you folks?
So actually we have different kind of thoughts. In his thoughts that District 2 is safer because there is a total number of injuries lesser than District 1. But sir, in my opinion, sir, District 1 is safer because sir, there is a less death. Because
Okay,
for us,
all right.
Yeah.
I understand. But when you go to the district collector, you cannot say this to the district collector. You just need to say this is a collective decision. You are the engineers or you are the leaders. You have to come up with one. So if you cannot agree, arm wrestling. You say who wins and you go with that. No, you have to come up with. So online, does anybody have a different answer? Here I see several people saying district 2 is safer. Anybody online have a different answer?
Yes, sir.
Okay.
So district A has less fatal crashes
Okay.
compared to district B. Yeah.
Okay.
So that's why group A is safer.
Okay. So
Might be injuries be there, but life loss is less here compared to second district.
okay, thank you, Shekhar. So I want to be clear that these are not number of crashes, these are the outcomes. So 5 is 5 fatalities, not 5 crashes. 6 is 6 fatalities, not 6 crashes. All right, so I see now district 1 has 1 person championing for that. Anybody else? So from a safety perspective, it looks like we have a mixed bag. Fatalities wise, district 1 is better, but major injuries wise and medium injuries wise, district 2 is better. Right. Total crashes wise, district 1 is better. So from a safety perspective, there are things, but every time you have a crash, we have secondary impacts. such as delays to traffic, so on. We haven't accounted for that, and in my discussions I am not going to account. So more number of crashes, you have more disruption to traffic. Okay. I will get back to this a little later. So the way that we have talked about safety so far this week has been primarily based upon the frequency or the count of the number of crashes. It could be per day, per week, per month, per year. We have looked at outcomes of crashes, fatalities, injuries, property damage, and the CAPCO scale. And then we also looked at, okay, who is involved: pedestrians, bicyclists, two-wheelers, buses, cars, trucks, so on and so forth. But all of this is based on either a count, or in this particular case, like I mentioned yesterday, look at percentages also, what share of the total. That does not tell the whole story. What we need to look at is some measures of activity or exposure. Just picture this. You have two scenarios. Scenario A, where you have 10 crashes. I am not going to say what type of crashes, just 10 crash outcomes. The same indicator in the other district is 20. Initially looking at it, 20 is worse than 10 because higher number of crashes or crash outcomes is worse. But like several of you said, hey, we need to know what the population is, or what the other better indicators are, how many vehicle kilometers of travel. District A had 10 crashes for let us say 1 lakh trips. District B had 20 but for 10 lakh trips. So you have 20 divided by 10 lakhs versus 10 divided by 1 lakh. So 10 divided by 1 lakh is a larger number than 20 divided by 10 lakhs, right. So when we normalize for exposure or measure of activity, in many cases we are not able to get actual vehicle kilometers of travel or vehicle miles of travel. For roadway sections or for areas such as a district estate, that is more appropriate. So what we tend to do is we likely will use other surrogate indicators such as per population, on average, or per vehicle. On average, every vehicle will travel 10,000 kilometers per year, a personal automobile. I don't know what the number is. Akhilesh, do you know what the number is in India? An average kilometers traveled by a car in India? 10,000, 12,000? Yeah, something in that order of magnitude. It's not 1,000, it is not 1 lakh. I don't think it is even 20,000 unless somebody is driving long distance every day. For typical urban driving, it would be somewhere between 10,000 and 15,000. Less than that. So I will use just 10,000 as a rough number. So if we can look at it by per registered vehicle, we can get a measure of exposure even though we don't have vehicle kilometers of travel. If all vehicles travel about the same, if we have a number of vehicles, that is a good indicator. Others include population. So the typically number of vehicles per capita is fairly stable over large area. 12 to 15,000, okay, thank you. So per capita is yet another indicator. We saw that in the first class around the world, what are the outcomes, because some places you don't even have good indicators of the number of registered vehicles. A lot of people who have their own ways of devising mechanical transport means. So but these are all reactive, not proactive. We are looking historically, what happened, what were the outcomes. If we want to prevent crashes, yes, we can learn from that, but we also need to look at near misses, near collisions, so on, and try to avoid that. So some of the surrogate safety measures include at intersections. These are particularly time to collision. If two vehicles had conflicting trajectories, unless you alert one or both, how much time to collision and how much in advance of that. So that's somewhat some of the advancements in the vehicle to vehicle, connected vehicle technologies, vehicle to infrastructure systems. Post encroachment collision time, time between when one vehicle leaves a spot and the next vehicle comes in. So somebody either stopped or sped up just to avoid that. So how close, how tight, how close a shave was that? Once again, these are typically at intersections. Deceleration rates, not the normal deceleration rates, for typical analysis for when you are looking at braking distance, we look at 11.2 feet per second square. I am using feet per second square, about 1.3 g approximately. For emergency braking, we may go to 0.45 or 0.5 g acceleration due to gravity. So these are normal, but can we then, based upon the sensors we have talked about, whether in vehicle sensor technologies or our mobile phones and so on, discern if anybody is braking at more than 0.5 g, we will call it an extreme event. If they are braking at more than 7 g, one level higher. So we can get those data. So we can look at it by individual, which is what the insurance companies do, or we can do it collectively for a region, for a roadway, for an intersection to see, discern, are there problems with the roadway design, with the signal timing, traffic control, or is it just user behavior there to come up with the appropriate intervention. Proportion of stopping distance ratio available to where are people actually stopping versus what you thought you had. So this comes with side distance, traffic signal timing, how much time are you going to give for your amber. So these are far more proactive and trying to look at events as they happen. They did not end up in a crash, but could have happened in a crash. So what can we do proactively to address this? So here are several things on this slide, and I will go over the figure in just a minute. Let's just look at the items that I have enumerated there. So measures of risk or exposure include traffic volume at intersections. It's not vehicle miles of travel that may matter. How many people are actually traversing the intersection, crossing the intersection? Motor vehicles, bicyclists, pedestrians, motorcycles, trucks, so on and so forth. Density, vehicles in a given unit of space. Congestion level, this is more on corridors, volume to capacity ratio, or the actual operating speed divided by the posted speed limit. If you have very heavy congestion, the operating speed is going to be much smaller than the posted speed limit. If you have very low levels of congestion, the operating speed may likely be even higher than the posted speed limit. Behavioral risk, speeding, distracted driving. So one of the advantages, and I will show you tomorrow, is some of the vendors that I have been interacting with in the last 2 years use mobile phone technologies to discern a lot of things that I've mentioned in the last 2 days, including abrupt braking, lateral longitudinal acceleration, deceleration, but they are also able to discern, is somebody using a mobile phone when they are traveling? Not just that, is that person the operator of the vehicle versus a passenger in the vehicle? Is that person actually holding the phone in their hand or using Bluetooth? Are they actually looking at the phone, and if so, for how long at a time? And what is the longest glance? What is the average glance? So all that comes to the distracted driving. So they are able to discern that with the technologies that are available. Then we also have in-vehicle cameras that I mentioned yesterday, where original equipment manufacturers, OEMs, install that to provide feedback to the user saying, hey, eyes on the road, or looks like you're fatigued, your eyes are drooping. They do that, but they also collect it for their own analysis. Infrastructure is roadway geometric design, road conditions, traffic signals, signs. Professor Maurya showed several examples of chevrons, for example. Do we have the right amount, right places, right visibility, so on. Weather related is harder for us to control, but if we know that, can we communicate that to the road users in advance, particularly motorized road users? Maybe even 200 meters upstream is enough. If you have, in US we have lots of icy, snowy conditions. If there's a slick patch of ice, can they alert other motors saying, hey, slow down, there's something. Fog, which I believe you have plenty of fog issues here in the Northeast. So these are some examples. The chart on the right is a different way of communicating what I did yesterday. I showed you the likelihood of survival or likelihood of death of impact at various speeds, 30 kilometers an hour, 60 kilometers an hour, 90. Here what I have is on the x axis is speed in kilometers per hour, and on the y axis is probability of death. But we have 3 lines. The orange is pedestrian, the blue is a pedestrian or cyclist collision, the blue is motor vehicle to motor vehicle side impact, and the red, I'm sorry, this is pedestrian, this is side impact collision, and this is head on collision. So for the same speed, so if I want to look at a 10% likelihood of fatality, the pedestrian fatalities occur at 30 kilometers an hour, side impact at 50 kilometers an hour, or head on at 70 kilometers an hour. You could change it around and say, okay, for a particular speed, what is the likelihood of fatality at 50 kilometers an hour? Head on collisions is very low out here, whereas for bicycle side impact it is 10%, whereas for a pedestrian it's 90%. So there are different ways to come. Now I'll give you several next several slides are just data from the United States. These are not number of fatalities. Remember yesterday towards the end I said we need to look at proportions. So what we have here are on the x axis dates going back to 1975 through 2022, and on the y axis is percentage. The black line is the number of people or percent of people outside a vehicle who were killed. The green line is people inside a vehicle. So the outside vehicle are motorists, bicyclists, pedestrians, and not occupants of vehicles. So you see that it has been stable around 20 to 29% around here, but in the last 15 years what we are seeing is non-occupants of vehicles account for a higher proportion of the fatalities in the United States. There are many reasons. There are people trying to understand this. If you look at the literature, there are hundreds of citations that you can find. Here is crashes by severity. Once again I am just giving numbers, not rates. So here are data for 2021 and 2022. It's a busy slide. I'm not going to read everything. I want you to understand the structure and the essence of it. The first column is description: occupants of passenger vehicles, light trucks, SUVs, pickup trucks, so on and so forth, motorcyclists and pedestrians and bicyclists. The first set of columns is killed, 2021, 2022 percent, the change, actual numerical change and percent change. The second set of columns the same for the 2 years, the numbers injured, the actual change in numbers and percent change. So what you have is total occupants killed in 21 were occupants were 28,000 and non-occupants were 8,800 approximately. And within occupants you have in passenger vehicles there were 26,000, of which cars were 13,000, trucks were 12,000, so on and so forth. We can slice it and dice it. And here the changes are numbers in between these 2 years. There was a reduction of 716, which is 1.7%. Same way the injuries, reduction of 1,15,000 or 4.5%. And we can look at who is getting, give me one big change is non-occupants we are seeing increases. Yes, Ritvik? Yeah. So don't just go by the gross numbers, the total numbers, aggregate numbers. Try to get an understanding of who or what are contributing to the total numbers. Yes. No, even injuries are reported. Usually if there is a crash in the United States, the operator of the motor vehicle is required to stop and report it, make a call, or somebody else makes a call and wait until the police arrive. Okay. And in urban areas it is very clear during the daylight hours. There are others who will at least stop, even there are some hit and run cases. Rural areas it is harder, but rural areas we have much lesser pedestrian activity outside of some small conclaves. Bicycle activities, maybe people will ride in rural roads for a few kilometers, a few miles, but you are not looking at tens of miles. Very few people ride a bicycle more than 10 kilometers or so. Motorcycling in the United States is very small, and increasingly what we are seeing is over the last 20 plus years, since 2000, the age group of 40 to 65 are the heavier motorcycle, and they are recreational riders. They are not riding it to go to work or to go to the store or to, they just maza hai, so I want to ride. Weekend warriors, that's one of the terms. I digress. So this one gives you for 10 years 2013 to 2022 crash severity, number of fatal, number of injury, number of property damage, and total number of crashes. This is the numbers that at the bottom of the pyramid I showed you earlier in today's. So what you're seeing, it went up from 30,000 to 39,000. It seems to have stabilized 21, 22 in total number of fatal crashes, but fatalities will see in a number. Injury crashes seems to have reduced. There are some COVID implications in the years 2020, 2021 for sure that has disrupted travel patterns. So this is number of crashes, and in the exercise that I gave you earlier today, you want to know not just crashes but outcomes by severity. So number of people killed. So that's this column. The next column is the population of the United States in each of these years, and the next column is fatality rate per population. So that has gone up from 10.41, went up to 13 in 2021, came down to 12.6. Fatality rate per number of per 100,000 licensed drivers, per 1 lakh licensed drivers, because you have fewer licensed drivers than you have the population. About 65% of the US population is licensed. Others are either too young, or some after the age of 70 or 75 they voluntarily give up, and there are a group of people who may be denied their driving license because of medical conditions, and there are others we talked about, repeat violators whose licenses. So that's why these numbers are about, this is about 65% of. So you see the rate per 100,000 drivers is been going up. The last year there was an anomaly. Per registered motor vehicle, so we have 303 million registered vehicles for a population of 333, and a vast majority of these registered vehicles are four-wheelers or trucks or lorries. So those numbers are here, and ultimately what I think is a much better indicator, we need to break it down as fatalities that occur within the vicinity of an intersection and fatalities that occur away from an intersection. For those that are away from an intersection or on roadway stretches, the crash rate per million vehicle miles of travel or 100 million vehicle miles of travel is a better indicator of exposure. How much are people driving, not how many people are driving. The extent, how many kilometers, how many miles are they driving is more important. So there you see the numbers from 1.1 has been steadily increasing, and these are much higher than the Western other westernized countries. Ritvik, did you have a question? Speak up please so the audience can hear too.
So can you please explain the VMT?
Vehicle mile of travel. I'll explain. If one vehicle travels 10 kilometers, that is 10 kilometers vehicle kilometers of travel. If two vehicles travel 10 kilometers each, that is 2 multiplied by 10, 20 vehicle kilometers. So there we use miles instead of kilometers. It's the number of vehicles multiplied by the distance. So maybe one vehicle traveled to come here today 5 kilometers. So that is 5 vehicle kilometers. Another vehicle drove 12 kilometers. So now we have 2 vehicles, total is 5 plus 12, 17 vehicle kilometers of travel. Does that answer your question? Doesn't mean that every vehicle is traveling the same amount. We are adding up the total travel. At intersections we want to know the activity, the number of vehicles entering the intersection, number of pedestrians within the confines. But for the most part we have had a lot of difficulty getting data at the intersection level. We talked about it yesterday I believe, is it is all manual in terms of people sitting and counting on clipboards. In the last 5-10 years we are looking at more video data from cameras that are at intersections and using image pattern recognition. Our computer science colleagues, computer engineering colleagues help identify was that a person who is walking, was that a bicyclist, was that a motorcyclist, and do that. That's a little better but not as efficient. The next one, yes?
VMT, like if it gives like vehicle mile kilometer, the entire city, but how it relate to particular location or intersection?
For an intersection, vehicle kilometer, vehicle miles is not the right. It is the ADT, or the number of people traveling. So these are gross measures. What we do for vehicle kilometers of travel is, for a state, we want to compare state 1 versus state 2. Okay. Assam versus West Bengal versus, let's say, Odisha. What are the total injuries, fatalities, so on, and how many vehicle kilometers. We also break it down by rural roads versus urban roads. We can break it down by vehicle kilometers of travel on highways versus medium type roads versus minor roads. So it is more of a macroscopic level than at a specific intersection. But we can also look at individual road segments. In the US, we have fairly good data that we can get for roadway sections. We have 10 kilometers, what is the ADT there? That average daily traffic multiplied by the length of the road gives us the vehicle miles of travel. Here is the injury trends. The previous one was the fatality trends. Here are the injury trends. We are doing some measures of exposure. This is where I was getting at metrics instead of just looking at the raw numbers, raw frequencies, raw counts. What we need to look at is ideally per vehicle kilometer of travel, or per registered vehicle, per capita. If we don't have that, so these are the descending order of parameters. And these are also used to compare data. We showed in the first day, Europe versus Africa versus Southeast Asia versus America, so on and so forth. So those are the gross numbers or gross metrics. Here are the CAPCO scales that I have described to you previously. So on the right here we have the CAPCO scale, but on the left is another one called the abbreviated injury scale. So that goes not from K to O, but it's a scale of 6, but there is a fairly close correlation. 6 is fatal K, 5 is critical incapacitating, 4 is severe non-incapacitating, and then 2 is possible, 1 is minor property damage. How do we make use of this? There is a concept called value of statistical life. There are economists who have worked on this for years and years, and let me just walk you through here. Let me just say, in the year 2023, the value of statistical life in the United States was $13.2 million. Let me now convert that to CAPCO. Please follow me on the screen. So what we have here is, on the left, let me just go back to the left. So this was revised for 2023. If you look at it in 2012, the value of statistical life was 9.1 million, whereas in 2023 it is 13.2. Basically, it is in current dollars. Each fatality, each death is equal to $13.2 million is the way to look at it. Now, if we want to compare, okay, we have so many people killed, so many people with life-changing injuries, so many people with moderate injuries, so many people with minor injuries, and so much property damage. To bring it all to one comparable unit, one comparable metric, they've come up with a scale saying that if the value is 1 for a K type, the unsurvivable, a critical injury is 59% of that. So the dollar value is 59% of 13.2, which is 7.83 million. Next is a severe injury is 0.26, 26% of a person killed, and that means that is 3.51 million. So now, if you know what is the distribution of crash outcomes in different contexts or different scenarios, you can bring it all down into one numerical value in terms of what is the dollar value. I'm using dollars because that's what is in the US. If you can come up with comparable analysis in India, we can use the same thing. This will guide investments in safety, whether it is engineering, enforcement, education, so on and so forth. Just because district B had 1020 crashes, district A had 1000 crashes, doesn't mean that we have to spend a little more in district B than district A unless we do these detailed analysis. So now we go into weighted. So what I gave you was one example of weighting. This is another way of doing weighting. If you don't have the dollar values, maybe you have a focus group of experts from different disciplines saying, okay, if a property damage crash is equal to 1, how much more would you weight an injury crash? How much more weightage would you give to a fatal crash? So in this crude example, I said, oh, based on a focus group, the people, all of you in this class and online, agreed that if the property damage crash is worth 1 point, an injury crash is 3, and a fatality, an injury is 3, not an injury crash, and a fatality is 12 times as bad as a property damage crash. So if I had that, I can go say, hey, in a particular context, I had 1 fatality, 3 injuries, 5 property damage crashes. So what is the cumulative weighted value or impact of all of these crashes? So the 1 fatal crash multiplied by its weightage of 12, the 3 injury crashes multiplied by their weight of 3, and the PDO crashes, we had 5 PDO crashes multiplied by 1 gives us a weightage of 26. This is a very, very trivial or simple analysis. Absent information on the VSL, you could get a group of experts to say how would you rate it, and if they say no, you go from one district to another district, they say no, for us a fatality is 50 times more worse. For the local context that's okay, but you have to come up with common metrics if you're going to compare across regions, geographic regions, and these weights may change year to year. That's what I wanted to show in the previous one. VSL 10 years ago was $9 million, now it is $13 million. So you have to update it further, and I'm not going to go into the methodology. It does not mean that when a person dies, the cost to the family or society is $13 million. It's kind of that way, but there's a lot more that goes into the analysis. There's a team of economists at the US DOT. That's all they do every year is update these. I shouldn't say that's all. That's one of the critical things that they do. Now get together with your teammates, and I want you to do the analysis based upon the data that I have here. So the data I have is a fatality is equal to 13.2 million, a serious injury is 6.8 million, and a PDO is 1 million. Okay, no, not 1 million, it's 0.04. I'm sorry, I changed the number, pardon me. Please use the numbers at the bottom. These were from a previous years, so please use the last bullet. We have the same 1 fatal, 3 injury, and 5 PDO crashes, and using the 13.2 VSL for fatal, 7.83 for injury, and 0.04 for PDO. What is the total value? It shouldn't take you more than 10 seconds. Yes, Shayantan?
36.89.
36.89.
36.89, 36.89. All of you have good calculators and good fingers. My fingers are fat sometimes. Instead of pressing 2, I press 3. So I at least have 2 people who got the same answers. That's just to illustrate to you how you can combine these to come up with a common way of quantifying the impact of crashes. Yes?
In this severity means like the serious injury cases like versus fatality, so they had like half of the weightage.
Yes. So I will go back.
Yeah.
And
Yeah.
so the weightage is 0.59. So this comes from statistical and actuarial analysis.
Okay.
So all we need to know is what is the fatality, and then using these ratios you can come up with the other numbers.
Okay.
Yes, Ritwik?
Sir, who is the consumer of these estimates?
Oh, this consumer, we use it incredibly. in the United States. So if an agency, it could be a district PWD, it could be at the state level, it could be at the central government level, has $100 million to invest for safety improvements. They get applications for 10 times, 100 times that amount. So they don't have the money to fund all of it. So what they do is try to come up with a benefit to cost ratio. Project 1 is going to cost $10 million, and the benefit from project 1 is 20 million. So the benefit to cost ratio is 2. To capture the benefit, one of the things they have to do is the current safety number is this. If we do this particular project, we will save so many lives, so reduce so many injuries, so on. I'll cover that later in today's class. How do you estimate what would be the benefits? Another group comes up and says these are, so this is used to quantify the benefits. One of the benefits, these are the safety benefits. We quantify benefits for reduced travel time, reduced congestion. Because of reduced travel time and reduced congestion, we have reduced fuel consumption, we have lower emissions. So all of that go into the picture. So typically these are used for benefit cost analysis, and this could be used by government agencies, for NGOs to determine where they want to prioritize their activities or investments. Oh, it's used extensively. And in fact, in the US central government, federal government, they require that we use these VSL to document when we put in an application for funding. We have to use this methodology for the safety analysis. Did I answer your question? So this was 36.9 or something, yeah. Now I'm going to go back to the problem I gave you earlier today. The same thing, we have 1000 and 1020 total crashes in the two districts, District 1 and District 2, and what I have added here is VSL. And I'm going to give each all of you 2 minutes, okay, to tell me which district is safer, which scenario is safer. 2 minutes from now, please work with your partners. Maybe one of you can work on District 1 calculations, the other can work on District 2 calculations. So 2 minutes. Do it, I'll call on you. Tell me your name again. You told me that yesterday. I'm sorry. Nishan. Yeah. Is there anybody who needs more time? Ho gaya. Anybody online who wants more time, please raise your hand. So I don't see any show of hands. Anybody in this room who has not spoken, please raise your hand and I will call on you. Tell me your name again. Tell everybody your name. Yes. Please use the microphone. Ritesh, microphone de dena.
Good morning, sir. My name is Akshay Banolia and I am a PhD scholar from Infrastructure Engineering Management Specialization.
Okay. So what did your team come up with? Sir, District 1 or 2? I just want one answer. District 1 or District 2?
One for one, sir. 1321.
I don't want sentence. I just want District 1, District 2. You can only say 2 words.
2, sir.
District 2. Okay, you went with 1 word. How about anybody else? Which is safer? Come on. You agree or disagree? Agree? Okay.
Agree, sir.
Agree online. Okay. So I did the calculations and I come up with the following. District 1's cumulative VSL is 1.3 million or billion in this case, because the VSL is million. So a higher number is bad. You want a lower number. So even though District 1 had lower number of total outcomes, 1000 versus 1020, District 1 had only 5 fatal crashes compared to 6 fatal crashes. However, District 1's A and B type crashes significantly outweighed the corresponding crashes. That's what changed the thing. So you have to take all of it in. But sometimes we don't take all of this into consideration, and increasingly what we are looking from a safe systems approach is we want to avoid or minimize K and A type crashes. We are far more willing to accept the B, C and O type crashes. So any intervention or strategy or countermeasure that will reduce the K, the people killed, people who have life threatening injuries, will be given higher priority. So maybe we will not use the B, C and O in these analysis. So it depends on what is your objective, and many times when we look at submitting grant applications or proposals, I don't know what the term is here, for funding, you have to look at what is the objective. If they say we want to reduce fatalities, then focus on K. If they say we want to improve safety overall, then you use CAPCO. So focus on what the thing. They may also be more specific that we want to improve safety for pedestrians and bicyclists, then the numbers you use would be corresponding to pedestrians and bicycles, the crashes. Any questions on this approach? Alright, so building on this, there are two types of crash rates. Professor Maurya asked this a few moments ago, and a couple of you. One is when you look at intersections or specific location, the level of what we want to know is measure of exposure or activities, how many vehicles are entering, crossing paths. Basically what we are looking at is potential conflicts, for which we need to know the total number of vehicles entering, number of pedestrians entering. But in the United States, so far the pedestrians, we are treating them differently. The standard metrics are number of vehicles entering. So what we do is use the ADT, average daily traffic, to the closest point to the intersection to say, hey, that will be the thing. But I'll show you with emerging technologies where we can be far more precise than that. So here we are looking at annual crashes, total number of crashes every year, multiplied by million, because we are looking at rate per million. RM is million, EV, entering vehicles. So that's what RMEV is, rate per million entering vehicles. So if we do that, and on roadway sections we will use, instead of ADT, we will use VMT. ADT is average daily traffic. On a typical day, what is the total traffic count, and in the denominator we have 365 for the 365 days a year, because we are using annual crashes over a year. Whereas if we wanted, so for an intersection, this is a simple example, it had 23 crashes, the average daily traffic was 6,500. If you do the calculations that I have outlined, it says the crash rate is 9.7 crashes per million entering vehicles. So now you may want to compare multiple intersections to say which is safer or worse. Just because you had more crashes doesn't mean it is worse, but if it had a much higher level of activity or exposure, just in the previous example that we saw, it might be better, safer, relatively speaking. But as many of you said, even one death is one too many. Our goal is to try to get that to 0. Okay. Now if you are looking at roadway segments, corridors, long stretches of highways, not the number of entering vehicles, what is the total distance traveled by all vehicles combined? That is VMT, vehicle miles of travel. And typically we get VMT by looking at, just follow me, my hands folks. If there's a roadway section from my left hand to my right hand that is 10 kilometers long, and on an average day you have 100 vehicles that travel on this, the VMT is 100 vehicles multiplied by 10 kilometers, that is 1,000 kilometer vehicle kilometers of travel. That's what we do to estimate VMT in the US, is we get spot counts of traffic. But with today's technology we can get it better, because our mobile phones tell you exactly how far they travel. So in this example what I have is a roadway segment is 17.5 miles long, the average daily traffic is 5,000. On average you had 40 annual crashes, so the crash rate is 40 multiplied by, because we're doing million, 17.5 is the length of the roadway segment, ADT is 5,000 and 365 days of the year gives us 1.25 crashes per million vehicle miles of travel. So we can do this to compare 2 roadway segments. We can do this to compare 2 districts or 2 municipalities, 2 panchayats, 2 states. You take into account all the crashes in the state, and now VMT, we will have to do it, okay, on the national highway system this was the VMT, on the state highway system this was the VMT, and many times you will have to come up with estimates, you may not have actual counts. If you look at activities that are done by organizations such as the World Bank, the Asian Development Bank, so on, they are unable to get from the locals, so they come up with some gross estimates based upon population, number of registered vehicles, extent of roadway, economic activity, population centers, to come up with some of these estimates of ADT and VMT. Now transitioning to the highway safety manual, take your eyes off the screen. If you have not heard of the highway safety manual, please raise your left hands. If you have not heard of the highway safety manual, please raise your left hand. Daniel and team, did you hear the question? If you did not hear of if you have never come across the highway safety manual, raise your left hand. Keep it raised. You've heard of the online too. If you have not heard of the highway safety manual, left hand up please. Well, you can only show your hand, the emoji. At some point I'd like all of you to come have your camera on so that I can have a photo. Are you all willing to turn your camera on now? Let's just do that right now. Please turn your cameras on for the next 10-15 seconds till we can get a screenshot. And I'd like to see how you look. Thank you. Others? Okay, I'll go with whoever I have. Thank you, Tushar, Pratyush, and no, keep it on, Tushar. I want to get some photos. Yeah. Hey, I'm looking at you. I don't want them to have the back of my head. I want them to see my head. Okay. Anybody else willing to turn on your camera? Aishwarya, Ashutosh, Krishna Kishore, please. All right. So, mil gaya? All right. So our AV people have got it. So I also want to take an opportunity to thank our audiovisual team for their technical support and keeping the room at the right temperature. Okay. Now I told them to keep it a little cooler so you'll be a little more alert. Just kidding. No. Thank you all for turning your cameras on. So the highway safety manual is something that's been around now since 2010 in the United States. It's patterned after similar efforts around the world. And in the next several slides I'll describe it, and it is used extensively. Once again, to come back to your point, Ritvik, about how do we use what I just showed you, is how do we document, okay, if we did this project, if we did this change, this intervention, the number of fatalities will decrease from 12 in 5 years to 10 in 5 years. There are ways to look at. So this has certain approaches or methods that will help you estimate the benefits. So the highway capacity manual, I will go through. It is a predictive tool. Hey, let me ask my faculty colleagues, if I give the PDFs to you during the breaks, I can convert it. When might you be able to share it with the participants of my slides?
So we can like just combine it and share it today itself.
At the end of the day today, or
yes.
Yeah, okay. I've been meaning to do that. So you don't have to keep taking notes. I just wanted to make sure. So the next several slides have a lot of text in it, but I will speak to them in a few seconds per slide. Bottom line, what I haven't read here is it provides and offers a set of predictive tools to estimate the frequency of crashes and the severity of crashes due to different types of interventions of safety improvements. So here are the steps. I'm not going to look at it, describe it in detail. The first is network screening. So you look at what you have. Then the diagnostic and countermeasure selection. So network screening also identifies not just the roadway types, divided roadway, not divided, rural, urban, roadway characteristics such as speed limits, number of lanes, freeways, non-freeways, I don't know if I mentioned that, and where you have crashes, how many crashes, what types of crash outcomes. Based on these, the second step is to come up with what would be potential countermeasures, and for each countermeasure what would be the benefit, and based on the benefit is the economic appraisal, exactly the point you asked, Ritwik, what would be the difference in, and then after we deploy it we evaluate, did we actually achieve the gains that we projected that we would get. If not, we will go back, feed that information into all the data that goes into the highway safety manual's methodological approach to say, oh, we thought we will have a crash reduction of X, now it is X minus delta based upon hundreds of such deployments. So it has what is called crash modification factors, and I will talk to you about crash reduction. There is a whole catalog saying if you did this in such and such a context, you will reduce the crashes by this amount. So the highway safety manual has 4 parts. The first one is introduction, part A. Part B is the management, safety management process. Part C is where I will focus a little more, and part D is the crash modification factors. The C is methods, D is the factors. Did Dr. Pulugurta cover any of this when he was here on safety?
But
this audience is different. Yeah.
Different. So
okay.
That was like 3-4 years back.
Okay. So I'll let you folks read what are these. Let me go into more of the details. So the predictive method is to come up with what are called safety performance functions. What they do is enable the analyst to come up with an estimate. I want to make sure that you all understand that these are, we are coming up with estimates of what might be benefits. What is the average? Once again, it is not, oh, you deploy it and in 1 year I didn't have that. It is meant to be much longer term, for many years. What do you have? On a network, it could be an area or similar types of roads in a particular district or in a state. It could be a very specific facility where you have an intervention, the national highway that is going from here to there. It did not have some of these features. Maybe it is rumble strips on the edge. We are going to put rumble strips over the next 30 kilometers on the national highway. So what might be the safety benefit? The rumble strips may be appropriate because we saw that we have a lot of run off the road crashes. So the intervention or countermeasure is going to be based upon the type of problem you had. So far we talked about a lot about type of crash, fatality, injury, so on, but both in my presentations yesterday and Professor Maurya's presentation, we went over the accident report that describes in greater detail what actually happened. Was it a single vehicle crash, head on, side swipe, T-bone crash, where did it happen, daytime, nighttime. So the strategies or interventions or countermeasures would be based upon a collection of these factors. So we look at that, and table 1 chapter let me go to the next. So I'll walk you through this. Table 1 in part C has predictive methods for different types. Chapter 10 is focused on rural 2-lane 2-way roads. Rural roads, not urban, 2-lane roads and 2-way, no divider, no separation of traffic. And there for chapter 10 you have now undivided, again you don't have divided just by definition of that, and so that is the roadway segment. And if you have junctions or intersections, what is the stop control on the minor leg? So this is the major street, you have minor streets. Do you have 3 approaches, 4 approaches? Is it signalized? Because even a 2-lane road, rural road could have. But keep in mind, all of these are based upon the US and Canadian context for the most part, and some may be from other parts of the westernized or developed countries. So please be very, very careful. Do not use those factors. Just say, oh, the CMF from the highway capacity, highway safety manual said this. That might not be appropriate in Ethiopia or in Bangladesh or in India or in Sri Lanka. That's something for research opportunities. If you're all looking for your master's and your PhD topics, can you look at these to come up with what are the benefits? Here was a problem, the state PWD or the National Highway Authority did such and such, and afterwards this were the outcomes, so you can document. The next chapter 11 is rural multi-lane highways. So multi-lane highways could be either undivided or divided, and once again you have stop control on the minor approach, 3-leg, 4-leg, or signalized on 4-leg. And then chapter 12 is for urban and suburban context, arterials. So you have all of it. It could be undivided, it could be divided, and you have stop control or signal control, 3 or 4 approaches. So this is the framework. When you look at the tables that are in chapter in part C of the highway safety manual, these are the ones that you need to look at as appropriate. So we are looking at the estimated, what is the expected number of crashes on average over an extended period of time. If you do not have any crashes, maybe you are building a new roadway where nothing was connected before. So you can use comparable scenarios elsewhere to say, okay, if I built it as a 2-lane without rumble strips, what might be it? Well, to build the rumble strips for the next 30 kilometers, it is going to cost me so many lakhs of rupees. But by building this rumble strips, even if I spent, let's say, 30 lakhs of rupees for 30 kilometers, we will save 2 lives over the night. So now you do the benefit cost analysis. This is the cost, this is the benefit. The basic elements that we need are historically what have we had for a specific site. I keep coming back, so what is it, right? Rural, is it intersection, is it 3-legged, 4-legged, so on, as stop control, traffic signal. Is it a corridor roadway segment? So be sure that you are using the right context. And this is based upon, if you haven't studied it, the empirical based method of analysis to combine the estimation based on statistics of historical observed data to come up with what might be in the future. So the safety performance functions are used, and then let's see, and the crash modification factor is the ratio of the effectiveness. Rather than going through the definitions, let me give you some numerical examples. I have 2 more slides with some definitions. So there is yet another term called the calibration factor. At this time I am going to say just assume calibration factor is 1. Nominally it will be close to 1, saying okay, in district 1 or in city A this was it, but city B has got some minor differences, so instead of it taking exactly what it was, it will be 0.99 or 0.98 or 1.02, 1%, 2%. I do not expect that factor, the calibration factor, to be 5 or 10. It is going to be close to 1. For our discussions here, just assume that is going to be 1. You know what happens when you assume? How do you spell assume? A-S-S-U-M-E. You make an ass of you and me. So the method is, on the left hand side of the equation we are predicting what likely would be the predicted number of crashes for a particular year and a site based upon the predicted average crash frequency for the base with the SPF for the particular type of improvement. CMF 1, 2, 3, maybe you are doing 2 or 3 or 4 safety improvements. So we have a CMF for 1, CMF for 2, CMF for 3. So it has got a multiplicative effect. And the last CX I told you, just use that as 1 for you. Now for each facility type we have the crash modification factors. Let me go to the example here. Is this screen visible on the, for those of you who are online? The table, are you able to read the table? If you are not able to read the table, please speak up. Not hearing that, I am going to proceed saying that you all can read it. So what do we have here? It is a particular table for crash modification factors to provide a median on multi-lane road. So the treatment or the engineering countermeasure is you are going to provide a median to separate the opposing traffic. And the roadway setting, if it is urban, arterial multi-lane, rural multi-lane, we do not know what the traffic volume is, because again some of these countermeasures are applicable if you have low volume, medium volume, high volume. So you will see different numbers based upon the different volumes. And so what we have here is the accident type or crash type, severity type. For all types, the crash modification factor is 0.78. For all types of injury, non-injury, it is 1.09. For urban, rural, all types of injuries is 0.88, non-injury is 0.82. So look at this non-injury here, it is 1.09, greater than 1. In the previous slide I showed you it's a multiplicative factor. If the value is greater than 1, what means is that crash number is going to increase. Why would we want to do that? Because we are going to reduce by 22%, 78% the injury crashes. So going back to our VSL calculations, the benefits that we derive from reducing the injuries outweigh the disbenefits or the costs by having non-injury crashes. So not everything that we do will always have a positive outcome. There will be some that we do. Whereas in the rural setting, it is positive in both whether it is for injury or non-injury. Is there anybody who did not understand this concept? Ritvik, no? Let us say we are going to provide a median and it is on an urban roadway. And by providing a median, historically we had 10 injury crashes per year and we had 20 non-injury crashes per year. That is the baseline. But by providing a median, the expected number of crashes that have injuries is going to be 10 multiplied by 0.78 or 7.8 injury crashes. By providing the median, the non-injury crashes, what was the number I used, 20? 20 is going to go up by 20 times 1.09, so 21.8. So we have a reduction from 10 to 7.8 on average for the injury crashes and an increase from 20 to 21.08. Now we use the VSL value for injury crashes, that was 5 million, for non-injury crashes it was 30,000. So multiply the two. The benefits of reducing the injury crashes are much higher than the increase caused by the injury crashes. Ritvik, is that clearer now?
Now it's clear. So just can you reiterate, how did you get back to the CMF here?
So these CMFs are based upon dozens and dozens, if not hundreds, of observations at various places across the United States. They had a problem, they did a certain treatment, they saw what was the situation before, they documented what was the situation after, and then they come up with this. In this case, maybe a median. There were hundreds of locations where there was no median. Before the median was there, here were the safety records. After they put in the median, here are the safety records. So it's based upon data. And that's what I said. Maybe in your jurisdiction, you did this and you found that I don't have 0.78. The benefit I got was a reduction of 85%, not 78%. I mean, a reduction of 15%, not 22%. You report that. Azaki may have said, okay, in my thing, I got a reduction of to 0.75. Somebody else may say I got a reduction to 0.66, somebody may say 0.93. So all this database is continuously updated. It's just not set in stone. So let me go. So here's what I had told you previously, the crash rates at intersections based upon million entering vehicles and roadway segments is per VMT. How do we apply that to the crash reduction? So what we have here, please follow me on the screen, is the crashes prevented were the number of expected crashes if the countermeasure was not implemented. So all the multiplication on the right side will be 1, right, before and after will be exactly the same. But now if we implement a countermeasure, the crash reduction factor is CR, and the ADT after improvement and ADT before improvement, we want to account for is there a change in traffic volumes also. So that will be it. So for each countermeasure we will have a reduction factor. So if you have multiple countermeasures, how do you account for all of that? This combined CR will be CR1 plus 1 minus CR1 times CR2 plus 1 minus CR1 multiplied by 1 minus CR2 multiplied by CR3. I will work out a couple of problems to illustrate how you apply it. But the point here is why we have the 1 minus thing is we have already accounted for CR1 thing. So that is why on the second term we have 1 minus CR1 multiplied by CR2. The third term we have already accounted for CR1 and CR2. So it is 1 minus CR1, 1 minus CR2 and then CR3, so on and so forth. Is there anybody who did not understand this concept? If so, please speak up. Okay. So let me go through some examples. Here over many years, I am not saying how many years, there was a 2-lane roadway that on an average had 10 crashes per year. To improve the situation, we are going to do 2 engineering interventions or countermeasures. The first intervention is we are going to widen the shoulder. The shoulder was too narrow, we are going to widen it. I did not say by how much are we widening it, by half a meter, 1 meter, 2 meter, does not matter, we are widening. And the second thing is we are installing a rumble strip. To me what this means is the problem was vehicles were running off the road. So that is why the widening the shoulder and the rumble strips are appropriate countermeasures for that. So now we have 2 treatments, and corresponding to the 2 treatments, how do we apply the CRFs? So for treatment 1, the crash reduction factor is 0.14, and for treatment 2, the crash reduction factor is 0.15. So what is the combined benefit that we will derive by implementing these 2 countermeasures? So just as I said at the bottom of the last slide, the combined CRF will be 1 minus CRF1 times 1 minus CRF2. And here's an, if you haven't seen what a rumble stripe, this is actually a rumble stripe where you have the rumbles and the paint on top of it. A rumble strip would be the rumble is outside of the paint, the difference between a stripe and a strip. So the calculations are as follows. It gives me a cumulative crash reduction factor combined of 0.27. We had 0.14 for 1, 0.15 for 2. So it is not 0.14 plus 0.15, which should have been 0.29 using the formula. The combined effect is 0.27. Another example, same, we have the 10 crashes per year, but here are more specifics of the types of crashes. 4 were run off the road crashes and 6 were head on. 4, the vehicle just left the roadway. 6, you had a head on collision. So the countermeasures were shoulder rumble strip and cable median barrier. The shoulder rumble strip will only help excuse me, address the run off the road. The median separating will only help address the head on collisions. So logically the crash reduction factor that corresponds to the rumble strips should only be applicable to the 4 crashes that went off the road, right, and the median crash reduction factor should be applied to the crashes that were head on. So that is how we would apply it. So for treatment 1 the reduction factor was 0.15, and for treatment 2 the reduction factor is 0.44. So what we have here is we had 4 out of 10 crashes that were run off the road. That's what I have in red. The black underline is head on. So the 0.14, I have a typo. I told you my fingers are fat, so this should be 0.15 here. Okay, 0.15 multiplied by 4 run off the road crashes out of the 10, or 40% of the crashes, and 0.44, which is a crash reduction factor for the median barrier, which will help address 60% of the crashes, 6 out of the 10. So the combined benefit is 0.32. Ishita, are you clear with this? Thank you. Is there anybody to whom this approach is not clear? That will have to do more behavioral changes. It's based on, we did this, how are the road users responding? Or maybe combine it with others, better lighting. So for each CRF, unless the users respond to the treatment differently. So you're looking at millions of users who are doing this. So one person changing behavior may save a life, but overall aggregate, it's not so easy to change the CRF.
Yeah, but sir, I still want to know one thing. So let's say this gets implemented.
Yes.
Now you start monitoring again the crashes.
Yeah.
And it definitely shows that the crashes have reduced.
Yes.
Good. Let's say the crashes have come from a different factor.
Yeah.
Not unanticipated, right? So then what is the decision? Should we try to change the CRF? What should be our
No, the
objective?
CRF will not change. Okay. So what we will have to account for is, the question was what happens? Well, we have the benefits by reducing the number of run off the road crashes and head on crashes. However, we had a few more rear end crashes, let us say. What can you do to that? Well, the intended benefits were accrued from the 2 that we had. The unintended was rear end crashes. I don't know, I'm just using that. So what else may you add? What other countermeasure may you add? Or if there is clear evidence that these 2 countermeasures are indeed causing more rear end crashes and we cannot do anything to mitigate that, now then you have to verify, say, like we did the VSL, the benefits from these reduction of these 2 crashes is so many dollars, the disbenefits from the rear end crashes is so many dollars, which is better or worse.
But we can use a visual also, right? On the road now.
What
Like many roads have those prone to accidents.
Yes, yes, we can add. So that is yet another countermeasure. That's a signage. Okay, add signage.
So that will not change the CRF.
No, that is because you had another countermeasure.
Ah.
Okay, that's not due to this countermeasure. You're putting more chevron signs, let us say. Okay, I've got 2-3 minutes. Let me give one more example. Here is a situation where we have 12 crashes at an intersection. Not 5 are left turn crashes and 7 are angle crashes. Again, I'm using different colored fonts to help you track. For us, left turn in the US is the same as right turn here, okay, because we drive, as far as people in India are concerned, on the wrong side of the road. So 5 left turn crashes and 7 right angle crashes. 2 treatments. Treatment 1 is to create a positive offset to left turn. So this is the geometric design. You're offsetting the left turn lanes so that there's better sight distance, line of sight for approaching traffic to look at opposing through traffic. Treatment 2 is we are adding a 3-inch yellow retroreflective sheeting to the back of the signal head. I haven't seen much of that in India. You have a typical signal head, but behind that we use another color contrast to improve its visibility. So now very clearly, not all of the treatment is going to be for. Left turn has a CRF of 0.38 that will be applicable to this 5. The retroreflective sheeting is going to be applicable to all. It affects the left turn as well as the angle crashes. So this is an example where I wanted to use. One crash reduction factor is applicable only for one set of problems. The other crash reduction factor applies to both situations at hand. So the 0.38 applies to the 5 out of 12 crashes. So I am just getting a proportion, whereas the reflective treatment will benefit both problems. So the combined CRF is 0.31. So I had inserted this blank slide saying that I will be here approximately at 11. We can break now.
Yes.
And I have more slides that I will cover in the next lecture. I told them that I have more slides that I don't intend to cover all here. Some of it is for this afternoon and some of it is for tomorrow morning. As we talked about, we may try to address some more today.
Yes.
Any comments from the, yeah, before I take a break, questions, comments, concerns, and I was going to ask for administrative comments. Any questions, comments, concerns? Yes.
Sir,
Speak up.
as you have talked about safety performance function, as we also say it is a performance indicator in the highway safety manual.
Yes.
Sir, the nature of the performance indicator for the sections and the intersections will be same or not, sir?
No, they are different. Each one has to be handled differently. Roadway corridors, we come up with different treatments, different solutions for problems. At intersections it is very different, so we have to evaluate each one separately. Unfortunately, I don't have time today. There's a whole class, one semester long class that I lead on safety and the use of the highway safety manual. I'm trying to cram that in about 90 minutes for all of you.
Yes.
Online, any questions? Okay.
No, sir.
Yes?
No, sir, no questions.
Yes, does it?
Thank you. I mean, sir, no questions. Okay, it's okay.
No, if you have a question, I'm happy to address that.
No, he said no question.
No question. Okay, all right. I thought you said I said.
Sir, I have one question here.
Okay.
Hello.
Yes,
Yeah.
Ritesh.
As we have seen in your slides that accidents causing a huge economy loss.
हाथ दिखा पहले.
Crashes are causing huge economy loss.
Thank you.
So we know that the maximum crashes are happening because of the overspeeding
Here in India.
in India.
Okay.
So can we reduce the speed and the severity will be reduced? So in US, is there any study that comparison between the economy loss by reducing the speed, because there will be loss because of the time value and money?
Yes.
So what will be the difference in the loss of economy by reducing the speed or versus the severity which is causing the economy loss?
That's an excellent question. The question for those of you online is that at higher speeds, the safety outcomes are much worse. So one way to improve safety is to reduce the posted speed limits or lower the operating speeds by using whatever techniques. So we may improve safety. However, when you improve safety, the travel times, when you reduce the speeds, travel times are going to be greater. What is the trade-off between the loss of economic value from the increased travel times versus safety benefits? Off the top of my head, I do not have any references to comment on that. I would recommend that you go to TRB, the Transportation Research Board website, look at TRID, their Transportation Research and Information Database, and do a quick search. It is free for anyone to access, but I suspect there are plenty of studies that have done that. I haven't explored that. I'm sorry. TRB, Transportation Research Board.org, and within there you will see a number of links. At the top you'll see a banner and it says database and resources, and within database and resources, TRID, Transportation Research Information Database. You can query. That is perhaps the most extensive reference or resource to identify any transportation related. It could be law, it could be public policy, it could be health, and of course engineering. And you should be able to access at least the citation, the abstract, and for the most part depending on who the publisher is, you will be able to get access to the publication. But some publications may charge you access. I do not know what the IITs here or the NITs or the other institutions have for subscription to, if it is an Elsevier journal, TRB is not going to make it available for free to you. You have to go through the copyrighted process for Elsevier. I'm just using that as an example. Yeah. All right.